Organizers for giving me a chance to speak here. So my talk will be on enumerative geometry. I'll say more specifically enumerative geometry of what. But first let me just tell you what is enumerative geometry. This is the basic type of question you want to ask is the following, that how many geometric objects are there that satisfy some constraint. That satisfies some constraint. So so what is the simplest example of such a question? The simplest example is you are given 2 points, how many lines pass through 2 points? So my geometric objects here are lines. So if I ask you how many lines are there are infinitely many lines. And my constraints are that they have to pass through the right number of, they have to pass through certain points. So if I ask you how many lines are there through 1 point, the answer is still infinitely many. If I ask you how many lines are there through 3 points, the answer is 0. So I have to impose the right number of constraints so that I expect a 0-dimensional space and hope that everything is transverse and it is sitting inside a compact, that this is a 0-dimensional compact space, and then hopefully I can ask how many and ask for that number. So passing through the 2 points is the right number of constraints. So, and you can, if those 2 points were in general position, then you can hope that this cutting down of constraint is transverse, and then you can ask how many are there. So this is a very simple question. A more interesting question is you are given 3-dimensional space and you are given 4 generic lines. How many lines intersect all the 4 lines? That's a more interesting question. The answer there is 2, and that question you can realize it. So this space of lines, you can think of it as a homology cycle in this Grassmannian, and this 2 which you get is basically some intersection number in this G24. So that's just an example. So the basic idea is that I'll formulate some enumerative question and I want to realize those enumerative number as the intersection of some cycles on some reasonable space. Not necessarily a manifold, but something close to being a manifold. That's the basic idea. And so now I'll be more specific and say what are going to be my geometric objects in this talk. So the geometric objects are going to be I'll first tell you the geometric objects and a little bit later I'll tell you what are the constraints. So the geometric objects are genus 0, and later on I'll make that genus G maybe, but for the to begin with I'll say genus 0 curves representing some class So I have some target manifold. So for simplicity, to begin with, we'll take X to be P2, CP2, and our homology class will be some D times the homology class of a line. But later on, I'll change this X, and much later I'll change the genus. But right now, let's say my geometric objects are going to be degree D curves in P2. These are my geometric objects. So what does this mean more precisely? I'm looking at maps from, so say Riemann surface. To begin with, this Riemann surface is a genus 0 Riemann surface to P2, or let's say X, and to begin with, let's say X is P2. And so when I use the word map, I'll always mean holomorphic map. So this map has to be holomorphic, and it has to be. I'm fixing the degree of this map. So U is holomorphic and U is degree D. What does that mean? That the push forward of the homology class is D times the homology class of a line, or more generally it is some beta in H2. This is my setup. So if I ask you how many degree D curves are there, of course the answer will be infinitely. There are lots of degree D curves. So I have to impose the right number of constraints so that I expect a finite answer. So motivated by this, let me ask the So the question I'm going to state is more than 100 years old. So now to keep things simple, let us take our target manifold to be P2 and my domain to be P1. So domain for most of the talk, the domain will be P1. So I define ND to be the number of genus 0 degree D curves in P2. So if I stop here, the answer will be infinitely many. So I have to make it pass through the right number of points. Now for the moment, just believe me, I'll explain later how I heuristically determine how many points there are supposed to be. So the expected dimension of this space is 3D minus 1 generic points. So from where did I get this 3D minus 1? I'll explain later. For the moment, just believe me that 3D minus 1 is the right answer, a right number. Okay, so this is more. So this question, so I'll tell you the history of this question shortly. But first, let me just interpret this number for you. So what is, sorry? Yeah, so this space, I was a little bit dishonest when I described this space. So I have maps, but I mod out by the equivalence that if phi is an automorphism of the domain, then U and U composed with phi are the same things. So I'll give a more detailed description shortly. So yeah, so if you have two distinct maps, they are not necessarily two distinct. I'm not necessarily going to think of them as two different objects. If they differ by an automorphism, they are literally the same things in a different guise. This is basically up to reparametrization. So yeah, sure. This is my actual space. So I'll give a more detailed description because I'll also be throwing in marked points. So I'll soon say more about this space shortly. Okay. But let's see for a moment what is N1. So that clock is not, excuse me, that clock is not strong. So what is N1? So N1 is asking how many degree 1 curves are there in P2. What is the another name for degree 1 curve? Line. Line is the more common name. How many lines are there in P2 through 2 points? So that everyone knows, that number has to be 1. What is N2 supposed to be? N2 is a little bit more delicate. Answer will still be 1, but it's a little bit more interesting answer. N2 is asking how many conics are there in P2 through 5 points. So what is another way to think of these curves? So I'm thinking of curves as I'm fixing the domain and I'm looking at maps and seeing what homology class they represent. But there is another way. There's another way to think about degree D curves. Look at homogeneous degree D polynomials. So now the discussion which I'm giving is exclusively for P2. I mean, so far, almost everything was, I said P2 just to simplify things. Now the following discussion is exclusively for P2. This homogeneous degree D polynomial is a homogeneous degree D polynomial in 3 variables. So what is a line? A line is the zero set of a linear equation. A conic is the zero set of a homogeneous degree 2 polynomial, and a cubic degree D curve is the zero set of a homogeneous degree D polynomial. So let's look at the space of conics. So conics, if I want to think of conics, I would think of it as something times x square, y square, z square, xy, yz, and so on. So you can count how many coefficients there are going to be. There are going to be 6 coefficients, but these are, if I scale a polynomial by some non-zero complex number, I get the same thing. So it is not 6 degrees of freedom. There are basically, it's basically a P5. 6 guys, not all of them 0 and up to scaling. That is P5. Okay, and so 5 is the right number. So I do want to, so I'm saying you have a general conic looks like this. Passing through each point will impose condition, and if those points were generic, there would be 5 linearly independent conditions. And so, yeah, 5 points is the right number, and so the answer better be 1. Similarly for lines, even for lines, the way to think about a line is, another way to think of a line is you have 3 coefficients here, but they are up to scaling, so basically it's P2. So lines is basically P2, and so passing through each point imposes a linear condition, and so you get 1. But if every time I could do this, then I would never get an interesting answer. It seems that by this reasoning, N3 should also be 1. But it is not. So let's see. So N3 is not 1. And let's explain so this question is an extremely hard question, and let me explain why. From this discussion, it seems that it's a trivial question. Every time you should get the answer 1. So starting from N3, it becomes an interesting question. And actually, even for N2, it's an interesting question. So let's look at the space of cubics. So you can write down all the coefficients, and the space of cubics, you can convince yourself there will be 10 coefficients, and so it is P9. Now, according to this 3D minus 1, there are 8 points here. So why do I have P9 here, and why do I have 8 here? If I want to ask the same question, it would be how many cubics are there through 9 generic points? That answer is definitely 1. There is no question about it. And yet here I have 8 points. So the catch is as follows. What is the genus of a degree D, of a smooth degree D curve? The genus of a smooth degree D curve is D minus 1 times D minus 2 over 2. And already you can now see D equal to 1 and 2 we were probably lucky with that. So the genus of a smooth degree 1 curve is 0, and so is the genus of a degree 2 curve. So for 1 and 2, we were asking basically these two were the same questions. But the genus of a smooth degree 3 curve is 1. And N3 is what? N3 I'm asking is that look how many cubics are there which I can realize as an image of a map from P1 to P2. Now, is it possible that if I pick a random cubic, it will be realized as a map from a P1? No. So the only possible way I can get a cubic in this way is if that cubic has a node somewhere. So N3 is not the number of, so if you were naive, you would say this is the number of cubics through 8 points. That is not correct. It is not the number of cubics, it is the number of cubics with a node. So 8 points cuts down the dimension by, so it is P9. So now you have 1 degree of freedom, and asking it to have a node somewhere is also 1 more degree of freedom, and that's asking it to have a node somewhere is no longer a linear condition. So already this is an interesting question. So this, and so similarly N4 would be the number of quartics with 3 nodes, and so on. Asking, counting the number of curves with certain number of nodes is a very hard question. So N3 is already an interesting question. So this number happens to be 12. I'm not justifying why it's 12, but the point is it's not 1. Okay? Any questions? All right. So, well, it has to be a single node, right? Because it has to be, so the genus of a smooth cubic is 1. So if it had 2 nodes, it would be irreducible. So it couldn't arise like this. And you have to see that, yeah, right. So just 1 node. All right. So hopefully the point of this discussion was to convince you that this is indeed a hard question. It's very easy to state, but it's a highly non-trivial question starting from N3. Okay, so now let me tell you the history of this question. The history of so this is more than 100 years old. So N1, N2, N3, and N4 were computed in around 1870 by Zoetzen. And I honestly have no idea how in 1870 he could have computed N4 or even N3 for that matter, because the proof I know there's no way it could have been that proof. I mean, it uses Chern classes and bundles and all that. So in 1870 there was no Chern class, no vector bundle. So I really don't know how he computed that at that time. But anyway, it's a fact. He computed in 4 as early as this, and so more than 100 years later, around 1990s, Concevich, Manin, and Riemann, they, using symplectic geometry, they found a formula, explicit formula for ND for all D. So more than 100 years to go from N4 to N5 or all ND. So this, so the, and more generally their formula is for, so the more general formula is for any del-Pezzo surface, they found this formula. So let me now explain. So right now the discussion was for P2. So what would be the more general version of this? So I said in general, I'm going to look at enumerative geometry of curves on some target space X, not necessarily P2. So what is the more general question? The more general question is the following. So fix a homology class. I'm asking how many genus 0 degree D curves are there in X representing the class beta that pass through the right number of points. Now the right number of points is as follows. I'll explain this later. It is C1 of Tx evaluated on beta minus 1. This is the expected dimension of the moduli space. So you can check that at least for P2, this is 3D minus 1. C1 of TP2 is 3D and then minus 1. Okay. Sorry? So this would be the general question. I mean, you would hope that for any X, this is a meaningful question. I mean, for any X, it is not a meaningful. So more precisely, Concevich and Manin obtain a formula for n beta where X is any del-Pezzo surface. So let me just say what is a del-Pezzo surface. So I'll not give you the definition, I'll just give you the classification of del-Pezzo. It is either P1 cross P1 or P2 blown up at up to 8 points in general position. So it's one of these 9 guys. And the definition is Kx is ample. That's the, I mean, that's the definition. From that, apparently one can prove this. So Concevich Manin obtain a formula for n beta for any del-Pezzo surface. Okay. So looking at rational genus 0 curves in any reasonable space is quite a well understood question. So how can we, now the next question is how can we make this question more interesting? This question as it stands is quite well understood. So there are two directions in which you can make this, generalize this. One is that you stick with, so one obvious generalization is you keep increasing the genus. That is one obvious generalization. Another generalization is, so I'll not talk much about that. I'll just, maybe the last few minutes, if I have time, I'll talk a bit about that. But another generalization is, so the fact is the moduli space of genus 0 curves is much better understood than moduli space of genus G curves. So if you stick to genus 0 curves, can you still formulate an interesting question? The answer is yes. Stick with genus 0 curves, make it pass through lesser number of points, but ask the curve to have some singularity somewhere. That is another way you can generalize this question. And so the first, so that is the question I'll talk about. So first question is, look at C beta. So what is C beta? C beta is number of curves through one less point. So see, this is 1 less than this number. So throw so many points. And if I stop writing here, then the answer will be infinitely many. There is a whole 1 degree of freedom. So I have to impose enough conditions so that I expect a finite number. So one way to add that extra condition is ask it to pass through one more point, which I do here. But there is no need to do that. Asking to pass through a point is not the only way I can impose a condition. Another way to impose a condition is that has a cusp somewhere. So cusp, by what do I mean that it has a cusp? So remember that I'm looking at maps. I'm looking at maps, so that means there exists a point in the domain such that derivative at that point is going to be 0. This is what I mean by cusp. Okay. And so this is the question I would like to, for the most of the talk, this is the question I'd like to discuss. But before that, let me just say what the other generalization. And so, of course, you can keep generalizing this, make it pass through lesser number of points, ask it to have higher singularity where you are depend more derivatives to vanish. So that is one question I want to think of in the future. And the other obvious question is, let's define. So let's put a G here. So when no G is there, G is understood to be 0. This is basically the same question. And so let me also put a J here. This is the same thing for genus G curves with a complex structure J. So remember, in P1 there is only one complex structure, so there is no need to write this symbol J here. But I now want to fix a domain, and that means I'm fixing a Riemann surface, not just the topology, not just the genus, but I have to fix the domain. Fix the Riemann complex structure on the domain. So let's denote that by J. Maybe the answer depends on J, maybe it doesn't, but for the moment, let's put the J here. So you fix the complex structure on the domain and make it pass through the right number of points. Basically the same question, but so for G equal to 0, it's basically this question. Okay. So this one, if I have some time, I'll talk about this. And let me just tell you what is known about these two questions, and then I'll start discussing this. So the main content of my talk will be this first question. So for question 1, C beta, and when the target is P2 or P1 cross P1, there is a formula for this by Pandharipande and Joachim Koch, and later by Zinger. So Pandharipande and Koch use an algebraic geometric method to compute this number. Zinger uses a symplectic method to compute this number, C beta for P2. And so we find a formula when X is any del-Pezzo surface by extending the method of Zinger. So this is with Indranil, Vamsi, Shen, and myself. So we extend the symplectic method of Zinger here. And I'll talk mainly about this. And for this question, G equal to 1, there is a formula for, so everything is for P2 now, by Pandharipande, and later by Ionel, using a symplectic method. So Pandharipande's method is algebraic geometric, her method is symplectic, and later for G equal to 2 by Zinger. And so for G equal to both 1 and 2 by extending Zinger's method, and X is any del-Pezzo, we obtain a formula for this, and this is again by Indranil, Varun Thakare, and myself. If I get some time, I'll talk about this, but I want to mainly talk about this question. Okay, so Now I'll talk in a more detailed way about this. I wasn't really very precise while describing this space. I'll now go to the details of this. Any questions? Sorry? They cannot really, it's not possible for them to be smooth. Just because the genus is 0, they at least will have self-intersections. But aside from the self-intersections, if I make them pass through the right number of points, they won't have any further singularities. But they have to have some self-intersections. Any other questions? So let me now start. So again, to keep things simple, I'll keep my target space to be P2, but later, those arguments can easily be extended to other target spaces. So P2 is an easy space to visualize, so that's why to explain things, I'll focus on the target being P2. Okay. So the first thing now I want to explain is moduli space. So what is my object? So the space that I'm going to consider is the moduli space of, so let's say my domain for the rest of the discussion will always be genus 0. So the first 0 denotes the fact that my domain is genus 0 and with some k marked points. Now, to keep things simple, I'll start the discussion with no marked points. The marked points will throw an extra layer of confusion. So first, let me explain the moduli space of maps. So the second 0 is the number of marked points. The first 0 is the domain. There's going to be a star on top. I'll explain what this star means later. And here you have X, which is the target space, and you have beta, which is the homology class represented by the map. So in words, this is the moduli space of holomorphic maps from a genus 0 domain to P2 representing the homology class beta. That is in words. Let me say this more precisely. So I was lying a bit. So that's not quite true. What I also want it to be non-multiply covered. So what is non-multiply covered, I'll say in a moment. So that is what the star denotes. So I'm excluding multiply covered curves. So this is, so I'm looking at, let's say, smooth maps such that, first of all, it represents the homology class beta. And I'm not really looking at smooth maps, but I'm looking at holomorphic maps. So what do I impose if I wanted to be holomorphic? I wanted to satisfy the Cauchy-Riemann equation. And I'm modding out by an equivalence relation. What is the equivalence relation? The equivalence relation is that if you have an automorphism of the domain, then U is in the same equivalence class as U composed with phi. That means that if I reparameterize something, they're really the same things. And so this is a slight lie. So this would be the definition of M, not M star. So M star is and U is non-multiply covered. So this is a technical point. I won't go into this. So the fact is that for reasonable spaces, so for example, when X is P2 or del-Pezzo or something, this. So I would like to say that this M star, this M is a manifold. Well, M is not a manifold. Those multiply covered curves are the troublesome points. So just remove the points at which it's not a manifold. And then this M star is a smooth, complex this is a smooth complex manifold of the right dimension. And what is the right dimension? The right dimension is C1 of Tx minus 1. So of course I have to explain a bit what is going on. So let me just interpret what I have written a bit carefully. So first of all, I'm looking at the reason I wrote it like this is deliberate. So first I'm looking at the space of smooth maps. That is an infinite dimensional space. And on top of that, you define this d bar. This d bar is the section of an infinite dimensional bundle. And the way I'm interpreting this is, it is the zero set of this section called d bar. And after a lot of analysis, you can, I mean, for reasonable spaces, so by reasonable I mean the linearization of this d bar has to be surjective at all points. And that is basically the saying that this d bar is basically transfers to 0. And if that happens, then everything is as expected, and the dimension of the moduli space will be the index of the d bar operator, which one can calculate using Riemann rock or Atiyah-Singer index, which is basically this. So this is index of linearization of d bar. Okay, so the basic point is that P2 is reasonable, del-Pezzo surfaces are reasonable in that sense. The complex, so if the complex structure satisfies that property, you call the complex structure to be regular. Okay. So the moduli space of, so you might ask why are we concentrating on del-Pezzo or P2 or what is so good about them? Well, that moduli space is quite well understood. That's the reason. Okay. So this M00 is a nice smooth manifold, smooth complex manifold of the right dimension, but the problem is this is not compact. My goal is, remember, that I want to realize my enumerative numbers as I will pull back some cohomology classes, integrate them on this and get a number, and I can't a priori do that because this is not compact. So the next thing is a compactness result. I mean, the next fact is that there is a nice compactification of this space, and on top of that, that is not a manifold, but very close to being a manifold, and I can do intersection theory on that. Now, before doing that, let me first throw in marked points. So M0K is basically the same thing. So I'll not write everything now. It is basically U, a map of degree beta, and K distinct marked points. And so the definition is self-evident, but the fact is what happens when there is an automorphism. So if there is an automorphism, U is same as U composed with phi. But what happens to the marked points? The marked points go to phi inverse of Y1 till phi inverse of Yk. So why do they go to this? That is because I want to define something called the evaluation map, which is take the curve and evaluate it on the marked point. And now you can see it is well defined. U evaluated on Y is same as U composed with phi evaluated on phi inverse of Y. So note that evaluation map is well defined. So now the next point I want to illustrate is that this M star is not compact. Let's say, so even without any marked points, this M star is non-compact. So let me illustrate this with the help of an example. So I'm saying that a space is not compact. Now, in order to show that a space is not compact, what I have to do is I have to produce a sequence that has no convergent subsequence. So I'm going to produce an explicit sequence for you. So I'm going to, point in P1, I can think of it as an equivalence class of two guys, X and Y. So this is a point in P1. And I'm going to produce a map in P2. Three guys will be there. So the sequence is as follows: X square, Y square by N, and XY. So this is a well-defined degree 2 map from P1 to P2. So let us say the coordinates in P2 are little x, little y, and little z. So you can rewrite this as saying that this defines the curve x times y is equal to z square divided by n. Now what happens when n goes to infinity? I mean, very naively speaking, what really happens when n goes to infinity? When n goes to infinity, you naively expect it will be basically a pair of two lines, x equal to 0 and y equal to 0, and that's basically good enough to say that there is no way this thing can actually be, even after passing to a subsequence, it cannot be, its limit cannot be, even pointwise cannot be the image of a map like this, from a smooth domain, a degree 2 map like this. Okay, so it's, if you think a bit, you will see that there is no, this sequence, even after passing to a subsequence, can converge. Okay, so, but very naively you see that it should, within quotation mark, converge to a pair of lines. So let's see exactly what is really happening. I mean, it's not compact, but let's see if we can sort of salvage the situation. So what is really happening? So as n goes to infinity, this basically goes to x square 0 and xy, and you can basically cancel off this x. For all points I can do that except for one thing, except when x is 0. So the fact is, so let me define one map, VA of xy, which is basically, if you forget this, call this 0 and divide out by x, this is x, 0 and y. And un basically converges to VA. So this statement is almost true. It will be true when I say outside one bad point, which is 0, 1. So outside this bad point, this is uniform convergence on all compact sets. And similarly, I can do a rescaling. So I can, remember we are looking at reparameterizations. So by the way, what I meant to say is not only can UN not converge to anything, even after reparameterizations, UN cannot converge to anything. That is what this example is supposed to illustrate. Okay, so I can, let's say I look at this UN, but in a different guise, I reparameterize. So my reparameterization will be the following. So let's say phi n is a Mobius transformation, which is x, ny. So this is a map from P1 to P1, so that's a Mobius transformation. So let's look at UN composed with phi n. So what is UN composed with phi n? You can convince yourself it's basically the same thing, except it's x square by n, y square, and xy. And so UN composed with phi n converges to VB, where what is VB? Where VB is the following map. It's basically the same thing. Kill this and divide out by y, which is 0, y, and x. So UN composed with phi n converges to VB everywhere except 1, 0. So 1, 0 is the bad point. So after rescaling, I can, so the first guy is basically, so it converges to what? X, 0, y. X, 0, y is basically the y-axis line, which is basically this line y equal to 0. And after rescaling, it converges to 0, y, x. This is basically the x-axis line. I mean, x equal to 0 line. Okay, so I produced two rescale. I mean, the initial guy was converging to y equal to 0, and after rescaling, it converges to x equal to 0. So now this leads to the following notion. So let me recapitulate. What I have said is I have described this moduli space of genus 0 curves. I'm restricting first myself to smooth domains, and if I restrict myself to smooth domains, I have a smooth complex manifold which is not compact. So the idea now is I will now set theoretically throw in objects which are maps not from a smooth sphere. So on this open part, so what I've defined is a well-defined topological space. I mean, it's a smooth world, there's a natural topology on this. Now I'm saying set theoretically throw in objects which maps from, say, a wedge of few spheres. So it need not break into just 2 things, it could break into 100 things, but the number of ways it will break is finite, let's say. So let's say we are looking at degree D curves. The sum total of the homology classes they represent is beta. So add these guys set theoretically, and the set which you obtain, let us call that M bar. So allow multiply covered curves as well and add these guys. So this is called M bar. So this is M00 plus maps from non-smooth domains. Okay, and so the problem with this is not a topological space. Now to specify a topology, I have to tell you what it means for a sequence to converge, and I'm going to sweep almost everything under the carpet. This example which I gave basically gives you an method to specify when a sequence, so you had a sequence of degree 2 curves, naively you were expecting it should converge to something which is a wedge of 2 spheres, their images. They should converge to a pair of lines like this. So, and the basic idea is it should converge to one of the guys everywhere outside a finite set of points, uniform convergence on all compact sets outside some bad points, and after rescaling it should converge to the other guys everywhere except finite set of points. So this can be made very precise. Okay, and that recipe for convergence gives you a topology on M bar. Okay, and so the big theorem is the following. So this is called the Gromov compactness theorem. The space M bar is compact. This is the big theorem, and so M bar is not a manifold, but it is very close to being a manifold because this is good enough for saying this forms a homology class. So I can now realize my enumerative numbers by pulling back cohomology classes, integrating on this, and getting numbers. Okay, so this is the big statement, and so now, so this space M bar is now available, and now I'll tell you how I'll make use of this M bar. So since I have some time, let me first say how I'll interpret Kontsevich numbers using this M bar. So first I'll now throw in, so I now want to interpret this number, the number of degree D curves through 3D minus 1 points. So I'll interpret it this way. So first of all, let's look at the moduli space of genus 0 curves through 3D minus 1 points. So I have 3D minus 1 marked points. So I'm looking at degree D maps to this, and we have an evaluation map to D minus 1 copies of P2. Okay. So now let me rehash that question. ND is the number of genus 0 degree D curves in P2 through 3D minus 1 points. Let me give them some names: P1, P2, P3D minus 1 through these points. So these are points in the target. Okay. So basically I now want to look at curves and with 3D minus 1 mark points. So these Y's are points on the domain. So these should belong to the moduli space such that u of y1 is equal to p1, u of y3d minus 1 is equal to p3d minus 1. I want to count the cardinality of this set. This is what I'm basically asking. But what is that basically saying? I'm saying that look at F inverse of, I'm just saying that pull back this point using the evaluation map, and I'm saying count the cardinality of that. What is that? What is another way of saying that? If this was compact, that is saying look at the degree of the evaluation map. So what is another way to say this? Let's ignore the fact that M bar is not a manifold, but let me write it in the following way. So these points, P1, P2, P3D minus 1, they basically represent homology classes. So I could have asked a more general question by asking a curve through a certain number of points where it intersects some lines or something. I'm just saying here it intersects points. I could make a more general question. And so let's look at the more, so this point defines a homology class. It's Poincare dual gives a cohomology class. So basically pull back the Poincare dual of the first point. And so this is the first evaluation map, and pull back the Poincare dual. So I'm basically given certain homology cycles in P2, pull back the Poincare duals via the evaluation map and integrate them on M bar. You can check that the dimension of this is same as the dimension of this. And this hopefully will be my ND. Hopefully that boundary is not going to contribute anything, and indeed it won't. And so I'm saying it this way because more abstractly this gives you a way to think of it in this following way. You are given some homology or cohomology classes. So P1, so the point itself is not important, the homology class it represents is important. So you have a point, another point, and so on. So instead of point, I'll think of it this way: L square, L square, L square. So L square means the intersection of two lines, which is a point. So the input is certain number of homology or cohomology class, and the output is a number. So this is a example of a Gromov-Witten invariant. So this is one way to, and these objects satisfy some nice algebraic properties. So you can think of this, they have this splitting axiom, which is basically a gluing theorem, and using that you can find the numbers for ND. That is basically the way NDs are calculated. Okay, so this is, since I had time, I spoke about this, but now the content of this talk is not to compute ND, but to compute the next number, which is number of curves with a cusp. How will I do that? And so now I have enough time. So let me now, so I'll not put all those decorations anymore. So let me rehash the question, which is, so let me concentrate on P2. The same thing goes for del-Pezzo. So CD is the number of genus 0 curves in P2 through 3D minus 2 points. So let me give them some names now. P, 3D minus 2 points, and in P2 that has a cusp. All right, so I have given them some names. So what do I want to exactly compute? It's the following. So let me first define this M. M is the following. It's maps and certain number of mark points. How many mark points? I should probably take 3D minus 2 mark points. No, I'll take 3D minus 1 mark points. So I'm looking at the moduli space of curves with 3D minus 1 mark points, not 3D minus 2, such that u of y1 is equal to p1, u of y 3D minus 2 is p 3D minus 2. What about the last mark point? No conditions. The last marked point is free to move. So why am I defining this place? You can easily guess. That is because this last free marked point is the place where I'll ask it to have a cusp. So this is my M. So I'll now, this last free marked point, I'll denote it by Y. So an element of M will now denote by this following symbol to avoid writing too much. So an element of M, I'll denote like this. I should put all these things actually, but I'll omit writing this. So you have this map which passes through these 3D minus 2 points and one free marked point, which is free to move. This is an element of M. All right. And so what is it I want to count? CD is by definition, it's the cardinality of the following set. These are maps in M such that the derivative vanishes. The unfortunate fact is that it has to rely on the open part M, not. So if I change this by saying this, uy that belongs to M bar, then the sentence would be wrong. Which includes the fact that what does du even mean on the boundary? Okay. So this is what I want to count. Sorry? Yeah, so this statement is false. This is a false statement because on the boundary also this derivative could vanish, right? Let's assume that it extends to the boundary, but if I count the cardinality of this set is not what I want. What I want is the cardinality of this set. That is the cause of all the problem, the M versus the M bar. Okay. So now what is going to be the basic idea? The basic idea is this: taking the derivative at the marked point, I'll interpret that as the section of some bundle and I'll compute its Euler class. So let me first state the basic classical fact, which I'll be, this is a classical topology fact, which is the following. Let V be an oriented vector bundle over a compact oriented manifold M. And suppose S is a smooth section that is transverse to 0. So the linearization is surjective. And also let us say that the rank of V is same as the dimension of M. Then the number of zeros, and so if everything was holomorphic, so the number of zeros, so everything is oriented, and the vanishing is transverse. So at each point where it vanishes, you look at nublines. It is either orientation preserving or orientation reversing. So S inverse of 0 is going to be a compact zero-dimensional manifold, a finite set of points. Count them with a sign. It will turn out in the holomorphic setting that sign is always going to be plus, but let me now just say the signed cardinality. This is going to be the Euler class of V evaluated on the fundamental class of M. So this is the fact I'm going to be using. So in my cases, everything is holomorphic, so the signed cardinality is the actual cardinality. And so the first place where, so now I'll cheat a little bit. I said M is a compact oriented manifold. My base space is not quite a manifold, but it is close to being a manifold. So this same sentence is true, provided this evaluating on the fundamental class makes sense. So that is one place where I'm going to cheat. I'm going to apply this theorem where my base manifold is not compact. And so now the idea is sort of now probably clear. I'm going to count the number of zeros of this section, this taking the derivative at the free marked point Y. I want to count the zeros of this section and evaluate the Euler class of some bundle. So the first question is, I can sort of see what the section is. The section is taking the derivative at the free marked point. I have to tell you what is the corresponding bundle. It's a section of which bundle? I can see the section, but I can't immediately see the bundle. So what is the bundle? I have to tell you that. So let's take a look at this. You have a map and you are taking the derivative at the marked point. So let's look at, so let me define this bundle. So you're looking at the moduli space of curves with one marked point. So to specify a bundle, essentially I have to specify the fiber at each point. So the fiber at each point, so an element is a curve and a marked point. The fiber at each point is, so this is within quotation marks, the tangent space at the given point. This is of course not, doesn't completely make sense what I'm saying because everything is modulo automorphism. What do you mean at the mark point? Why? There is no such thing as mark point. So the basic fact is this. So first look at the moduli space without any automorphisms. They're saying tangent space at the given mark point makes perfect sense. And that bundle descends to the quotient. That is what I mean by this. And the second fact is this bundle extends to M bar. So essentially the fiber at each point is tangent space at that given mark point. So this is called the universal tangent bundle. Universal tangent bundle. Okay. And so I have to just tell you this is a section of which bundle. So now it's more or less clear. du taking the derivative at the point is a linear map from P1 to P2. So it's a map from y to tangent space of P2 at u of y. So hence it's a section of the following bundle. So it's a section of T star P1 tensor TP2. It's a section of L star tensor F star of TP2. So F star here is evaluation at the free mark point. And so it's not hard to show that on this open part it is transverse. And so if I were doing wishful thinking, I would hope that so what I'm going to hope for is that this number that I have, CD, is going to be the Euler class of this bundle evaluated on M bar. If I were doing wishful thinking, this is what I would hope for. And this Euler class, by the way, note is computable. Why? Because this will basically boil down to the number of curves, rational curves through 3D minus 1 points, and that by Conservator's result we know. So using Conservator's fact, this Euler class is very much computable. And so if I were very lucky, then my number of cuspidal curves would exactly be this. And unfortunately, that's obviously not going to be true. Why is that? That is related to this fact. I want to, the zeros, the Euler class is going to give me wherever the section vanishes on M bar. I evaluated it on M bar, not on M. Okay, so the only way that sentence is true is if my section did not vanish on the boundary. So first of all, I'm saying my section extends continuously to the boundary, that's believable. But the fact is, does it vanish anywhere? And unfortunately, it will. So there are going to be these guys in the boundary. So you have a degree D1 curve, and you have a marked point. You have a degree D2 curve here, and you have a constant creature here. This guy is not stable. Okay, but if you put in a marked point here, now this becomes a stable map. So these creatures are going to be in the boundary. And so what is my section? It is take the derivative at the given marked point. So taking the derivative, so you have this constant map and you are taking the derivative at this marked point. Obviously it will be 0. Any reasonable extension will give you 0. So the question is, how much does this contribute to the how much does the boundary contribute to the Euler class? This is the really difficult part. And so this basically involves understanding this behavior of the moduli, constructing a neighborhood of this point and understanding this section in a neighborhood. So basically you have to perturb the section and count how many zeros are there, and that is the really challenging part. And so the multiplicity actually turns out to be 1, but this is the difficult part. And then, so your CD is basically the Euler class minus the boundary. And yeah, and so since I have, I guess, 3 minutes, so that time, is it correct or because? Yeah, okay. So I'll just take 1 more minute. I'll just say that this same idea basically is used to count genus G curves with a fixed complex structure. So there the idea is basically, so the initial idea is by Riemann and Chern. They introduced this concept of symplectic invariant. So remember my moduli spaces were moduli spaces of holomorphic maps. Now, holomorphic map means it satisfies d bar u equal to 0. So their idea is don't look at holomorphic maps. Perturb this d bar and look at solutions to the perturbed d bar equation and count the number of zeros with a sign. That number is called the symplectic invariant. Now the question you can ask is, symplectic invariant, is it the same as the actual enumerative number I want? And for genus 0, the answer is yes. So the genus 0 symplectic invariant is same as the enumerative invariant. Starting from genus 1, the answer is no. And the reason is as follows. So this d bar which you have is basically a section of some infinite dimensional bundle, and this symplectic invariant is in some sense the Euler class. And again, it's the same problem. The Euler class counts a little bit too much. There is some boundary component which gets counted in the symplectic invariant, and you have to subtract off this boundary component to get the enumerative invariant. And that's the basic idea. I mean, so INL does that for genus 1, computing the boundary component, and then Zinger does that for 2 and 3. We just extend Zinger's idea to del-Pezzo surface. And so, yeah, I'm done. So this number, to get the actual number, you use the splitting principle to compute this, and it will break down into computing, say, the intersection number of L square with M. Intersection number of L square with M is what? M is you have 3D minus 2 points. L square is one more point. It's the number of curves with one extra point. And yeah, one more thing is you have to compute the Chern class of the universal tangent bundle. So that you have to use a trick. You have to cook up a section of this, look at the zero divisors minus the pole divisors, and yeah. But so we don't use localization. I haven't actually thought about that question. Can you use localization to compute this? That's probably another interesting thing. It's a recursive formula. I mean, I can tell you the numbers for a few of these. I can tell you, for example, C3 would be same as the number of cubics with a, so C1 and C2 have to be 0. I mean, you can think a bit about that. C3 is same as the number of cubics with a cusp, and this one is, for example, 24. And then on its own, they don't have much. I don't think so. I mean, that same thought occurred to me, but somebody would have written some paper saying that, I guess. Yeah, it's too obvious. I mean, that 24 stays too much in the face for someone else not to have thought of it.